have
like,
to?
It was like on the floor.
Good. Okay, so, well, it turns out that this problem does not tell you what your emotional preferences are, but it does tell you the speed with which you can do these things. And in particular, we row at 2 miles per hour, and we walk at 4 miles per hour. And let's suppose that the thing we care about is that we do this route in the shortest possible amount of time. Okay, well, if that's the case, then what we are trying to do is minimize time. And to minimize time, there's going to be some point somewhere on the shore such that, let me make it a little more extreme, so that no one thinks this is a straight line, such that, and let's just call this point x units from the point, and this is what the problem does in the book too as well, yeah. And so this person is, in this case, we're not quite rowing as little as possible, but we're not doing much rowing. And then from that point on we do the walk. Cool? Okay, and the goal is to minimize time. And if we want to minimize time, then what we really need to do is to construct an expression which will tell us what the time is. All right, well, if this is x and the total distance is 3 miles down shore, then that makes this 3 minus x. And then that makes this root x squared plus 4, and this root 3 minus x squared plus 1. Okay, so the variable that I'm changing is x, and there'll be some sort of happy point where my time is minimum. Okay, good. Well, now I have to write an expression for the time. Well, distance equals rate times time, and so I can express the time for any simple trip in which I'm going at a constant rate as just the distance over r. And so I'm going to construct a time function. And the time function is going to output for a given x, the amount of total time that the trip takes. And the amount of total time that the trip takes is the time spent rowing plus the time spent walking. And all right, breaking it down this way, now I think I know what to do, right? Because what is the time spent rowing? Well, it's just the distance that I row, x squared plus 4, over the rate at which I row, which is 2. And what is the time spent walking? Well, it's the distance that I walk, which is x squared plus 6x plus 10, the square root of that, over the time, over the rate that I walk, which is 4. What's up? Plus 10.
Minus 6x.
You're right. Okay, good. So this, I think, was the hard part. Do you agree? Was just the thinking and the understanding, and even though they gave you the picture, so they made it kind of easier for you. All right, now it's just a calculus problem. I have a time function, and all I want to do is minimize it. So I need to find out where this function is smallest. So I'm just going to take the derivative. So I have a 1/2 because of the thing in the denominator. And then I have another times another 1/2. X squared plus 4 to the negative 1/2 back inside 2x. Plus a 1/4 times a 1/2 x squared minus 6x plus 10 to the negative 1/2 back inside 2x minus 6. Alright, and now we have quite a lot of algebra to do to figure out when this is 0. And I kind of just don't want to do this, but I guess I will. So this is x over root x squared plus 4. And there's another 2 in there somewhere, like there. And then this is, let's see, that 2 cancels one of those. So I'm still going to have a 4 down here. So this is going to be x minus 3 over 4 root x squared minus 6x plus 10. I think that's right. Cool? Alright, so when is this 0? I don't know. So I have to do more algebra. So let's see, this is x over 2 root x squared plus 4. And then this is going to be negative equals negative x minus 3 over 4 root x squared minus 6x plus 10. And this is an equation I don't really want to solve, but I will. So let's go. Let's just cross multiply, and the 2's cancel. So I get 2x root x squared minus 6x plus 10 equals x minus 3, and there's a negative there, root x squared plus 4, but the negative's about to die. Does everyone see what I'm doing? Just sending it to 0, moving one of the giant expressions over the other side, cross multiplying, now I'm going to square. So hopefully this all works out. So this is 4x squared minus 6x plus 10. And this is, now I'm starting to doubt myself. No. X squared minus 6x plus 9 times x squared plus 4. And then the negative just died. Alright, so now I think at least, I thought the quartic terms disappeared. They don't, do they? Alright, good. So 4x to the 4th minus 24x cubed plus 40x squared equals x to the 4th. Let's see, how many, I think, is it like 13x squared? I'm like kind of doing this in my head because I'm lazy. Minus 6x cubed. Wait, can I even do that? Yeah, I can. I only get one cubic term, and then I get 2 quadratic terms, and I'm gonna get, what the hell just happened? Minus 24x. I don't know why I thought this would be faster. Plus 36. I think I did that right.
Yeah.
Woo! All right. Does anything get any better?
Yeah.
All right. Good. So I get 3x to the 4th. I'm starting to remember this problem. Minus 18x cubed plus 27x squared plus 24x minus 36. Okay, who made it this far?
Woo! Barely made it.
All right, I can get rid of a 3, so minus 6x cubed plus 9x squared plus 8x minus 12. All right, and at this point, if you go to CalChat, they use a calculator and they find the roots. But I will not use a calculator. I will use the law of ones. Wait, does this work?
Yes.
1, -5, 4, 12, 12. Boom! Notice that textbook writers will often make 1 a root, and they have done so here. So this is x minus 1 times x cubed minus 5x squared plus 4x plus 12. And, like, I'm done. X is 1. Don't make me justify that that is a relative min. It just is. The answer is 1. Woo! Problem solved.
Very.
All right. If this were if you really, really wanted to make sure that this was a relative min, what might you do? Second derivative test. I actually think that would be easier than somehow coming up with a sign chart for this, which sounds like way more impossible, right? So I'm not claiming that the second derivative, it would probably take you another 3 minutes or something to take the second derivative, but then just plugging in 1 would give you something negative, and thus you would know there was a relative. Yes, Mark?
How do you know that none of the other roots are negative?
I'm hoping that this cubic just has no other roots, but I actually don't know the answer. Does it? Did anyone do this with calculator?
So you're just assuming that 1 is the root?
I am temporarily assuming
It sounds right.
it may have other roots. I'm not capital A assuming. I am punting the question because I don't feel like it's but I'm hoping that it doesn't. Subsequent, I will promise to check up on this next period. All right, good. What do we have time for? 3 minutes. Let's do the easiest other optimization problem you can think of. How about?
So that optimization is like 5. Is that also going to like the 2 triangles formed by your path at C?
What's up? No, because it's 1 and the other one is 2. Oh, yes. Oh, that's kind of like actually sort of interesting.
Shouldn't the both triangles be plus?
Wait, he's saying something kind of cool. Wait. Shh. he's saying that if the answer is 1, which it seems that it is, but I hope it's 1, right?
That's what the
Yeah.
book said.
That's what the book said, good. Then that means that's 1, and that's 2. In other words, these are like congruent triangles. This is actually kind of interesting because actually I could have sort of predicted this to be the case. How do I say this? Because there was a follow-up problem here, which said, okay, watch this. Which said to do it in terms of angles. Did anyone see this? They used the same picture, and they said, okay, now take this vertical line, call this like theta 1, and call this theta 2. Good. Actually, never mind that. Yeah, I don't have a deep answer for why the triangle should be congruent. I can't decide whether that's
We
a...
don't really accept it. It's a parallelogram. If we apply it to the guy, then we go under weight. You go a little bit, but then you just like drag it out.
I think it's more a feature of the fact that you can... It's because you walk twice as fast as you row that you want to spend...
No, but you spend the same distance on either one.
I know, but I think that the ratio between... I can't be sure, I'm not sure. All right, good class. Tomorrow we will go over anti-differentiation. Woo!